This video is about reductions with radicals. Now, these reactions technically are organometallic reactions or straight up metal reactions involving single electron transfer. However, as it's a single electron on the element, technically they can be referred to as radical reactions. Now, the first one we are going to see is the reduction of aromatic rings via a Birch reduction. The reaction conditions are relatively simple. Initially, you react your aromatic ring with sodium in liquid ammonia. These are horrible conditions to do in a fume hood. You probably need a glove box if you want to do it efficiently. And in a second step, you just add acidic water. Now, if you're thinking, whoa, do you really want to mix sodium and water? The answer is no. You have to be extremely careful and make sure that you don't have any excess sodium. And ideally, use most of it up with the excess aromatic compound. Either way, your final product is a cyclohexadiene. And notice that one of the two double bonds tends to be of the same carbon as your substituent. So here is a practice problem. Pause now. And here's the answer. Here's another practice problem involving phenol. Pause now. And here is a partial answer. I say partial because, as we can see, there is an enol, which of course is going to tautomerize to form a ketone, which is the final answer. The Birch reduction also happens to be the best way to reduce an alkyne into a trans-alkene, as it has exceptional selectivity. In fact, if you want exclusively trans-alkenes, this is pretty much your only approach. Recall that this is complementary to the Lindlar's catalyst, which will give you exclusively the cis-alkene product. Here is a practice problem. Pause now. And here are your answers. We can also modify the Birch reduction slightly by exchanging the sodium metal for lithium metal, giving us conditions that are very good at reducing the alkene of an alpha beta unsaturated ketone. For example, we can convert this chalcone into just a regular ketone. It is important to note that when reducing an alpha beta unsaturated ketone, the second step is adding a proton to the alpha position. Now, a proton is an electrophile, so theoretically we should be able to exchange that proton for any other electrophile, and we should see the electrophile add to the alpha position. And in fact, this is what we see. If we follow the same conditions with lithium and ammonia, followed by, say, an electrophilic carbon such as an alkyl bromide, we will alkylate the alpha position, giving us a complementary method to, say, a beta addition with a cuprate Grignard. Here's a practice problem. Pause now. And here's the answer. And here are 3 more practice problems showcasing what we've learned in this video. Pause now. And here are the answers.